So by lemma 1, we discussed the amplification of the identifiable distribution. Basically, it means that the Q, the expectation of the log density function, find the maximum at the parameter that we generate the data. So that's very nice property, which essentially justifies the using why MLE, maximum likely estimation, is reasonable thing to do. And so naturally we can expect that the sample version of the objective function, log-like function, should be consistent to converges to the maximizer of the Q set, right? But rigorously, what kind of condition we can? So is this enough? Turns out that no. The answer is that the convergence to Q theta should be uniform. Okay. And I like to emphasize that the identifiability is quite important, because if not, then the limit, right? So this is actually Q, so same thing. So Q theta is not, does not have a unique maximum at theta. So suppose it's a flat. That means what? Then the Q, the MLE, okay, Qn, even though the MLE exists, it doesn't really converge it. We don't know which one to converge, right? So it's theta 0. If you have a theta 1, theta 2, take the both maximum, then theta hat can, we don't know which one to go. So basically, if it's not identifiable, then theta, the limit point does not uniquely exist. So it doesn't converge. Okay, so this theorem 2.1 is a formal statement of the weak consistency. So as I said, uniform. So convergence should be uniform, and then identification condition, which basically is about the unique maximum. Okay. So I'm just let me just describe some give a sketched proof. So unique maximum at theta null means that you have a Q theta null should be the maximum. So Q set, okay, that means you can find Q theta null minus Q theta greater than delta for all, so for all, for some, right? So given epsilon, you can find delta such that these holes for all theta in the neighborhood, outside the neighborhood. So you have a theta null, then you can basically find the outside the neighborhood of the epsilon tunnel. Okay. So as long as it's outside, okay, outside, then right, then this difference becomes greater than delta. That's kind of argument. So So you can step 1 proof. Actually, you can find it a script. Okay, I created a script for your convenience, so you can feel free to use it. Okay, I already stated that. So Q zeta has a unique maximum at zeta equals zeta null is equivalent to saying that for all epsilon exists delta such that uh, Q zeta null minus zeta Q zeta is greater than delta for all zeta outside ball of the epsilon. Okay, should be no zeta. Okay, so that's step 1. Step 2. So that basically means that we can, because this is for all, so if we zeta hat is does not belong to zeta null, then it's because this is one implies this, right? So that means that in terms of probability we can say the same thing. So Q zeta null minus Q zeta hat, there's no n. Delta. Okay, that's a step 2. Step 3. This is more like a standard technique, but you don't have to understand all the details in this course. We are not really it's not our major interest in this course, but just for the curiosity, for the sake of curiosity, I just write it there. So this one, Q zeta null plus Qn zeta hat plus Q hat n zeta hat minus Q zeta hat, right? Delta. Okay. And then because this is the maximum, if you use different value is a smaller, but minus, so it's larger. Okay, like that. And then this is a little bit standard technique, but this is more like sorry, delta over 2 plus Qn zeta hat minus Q zeta hat delta over 2. Okay. Well, this is triangular inequality. Triangular inequality. Okay. and this is because Qn zeta hat is larger as Qn zeta null. Okay, so we can, by the way, this is positive, this is also positive by definition of the right, Q, because Q has a maximum at zeta null, so that's why it's positive. So anyway, we can now you can write it as a 2 times supremum of the Q n zeta minus Qn. And that is the we can make it small, right? So we can make it 0 goes to 0 because of the uniform convergence, uniform weak convergence. So that gives the proof. This is the convergence and definition of convergence probability. Okay. So as we discussed before, if this is not identifiable, then we don't have a unique, we may not have a unique maximum, and zeta hat may not converge to a single point. So identifiability is important for the convergence of the MLE. So that's the point. Interesting question is, what if the the true density does not belong to this class? Then okay, so we can still compute the MLE, right? Using a, because you can still assume some sort of the working model to construct the log-like function and compute the maximizer. So that's the zeta hat, and but zeta star converge, but this is not true parameter because the true density does not belong to this class. So what do you mean by zeta star? What is the meaning of zeta star then? That is the question. So we'll discuss this in the live class. And there's other properties of the nice properties of MLE, asymptotic normality and asymptotic optimality, which means that it achieves the lower bound, and Wilks theorem. So we'll, if you don't have any questions, I will cover this. But if you guys have questions, then I will answer the questions in the live class.